Today we'll be learning what's called the Central Limit Theorem. Now this is a very interesting theorem because what it says is for any quantitative data, if you take the mean, or if you look at the means of those data, it's going to become a normal distribution no matter what the data is. Okay, so let's dive into one of the problems to show you what I mean here. So let's say that at a certain school, in a certain class, these were the test scores of the students in the class. Okay, so I just need to explain a few concepts before I dive into the central limit theorem. So 99. Okay, so you'll notice that the scores vary very greatly, like from 10 until 99. And that is a reasonable assumption given the range of students in a classroom and the range of difficulty in a test in a classroom. Some students might perform very well, some students might not. And the same student might perform well on a certain test, but might not in other tests. And there's going to be a mean and a standard deviation for this data. Okay, so the mean here is 63.5. Okay, so that's not a very good mean. This class didn't do very well on the test. But the mean score of this class is 63.5. And as you can see, some of these scores are very, very far apart from the mean. And that is not unusual, such as 10 is very far away from the mean. 24 is also pretty far away from the mean. 34 is also pretty far away from the mean. I think 99, 96. I mean, these scores are kind of far away from the mean. And if you draw this on a normal distribution-ish looking graph, the mean is going to be in the middle. Actually, let me draw this graph a little bit smaller so to compare with the other graph that I'm going to draw. Okay, so the mean is going to be in the middle. And scores are pretty much all over the place right now. I think actually the graph is going to be less steeper because it's pretty well distributed right now. Okay, so this is what a graph of data here would look like. But let's look at some of the means of the scores. So for example, I'm going to underline the scores according to the student who took them. So these are scores actually of 3 different students. Okay, I've just mixed all the scores of 3. Oops, I need to erase this. I've just mixed in the scores of 3 different students, the test scores of 3 different students. So student A are these were the scores taken by student A. And these were the scores taken by student B. And lastly, these were the scores of the student taken, or test scores of student C. Okay, and you can find the mean of each of these students. So the mean right here is the class average, but we can also find the average of each of the students, right? So to find the average for student A, you just add up the red scores and divide by 4. And if you do that, you're going to get 55.25. And for the B, if you take the average, it's going to be 53. For student C, if you take the average, it's going to be 82. And if you look at, so these are the mean scores, right? These are the average scores. And if you look at the average score, they are much closer to the mean than each of the individual scores are. Right? So that's what the central limit theorem is saying. Instead of looking at the scores themselves, if you look at the averages, such as we're doing here, if you look at the averages, they're going to become more like a normal distribution. So if you graph the averages, it's going to look more like this. The scores are going to be much more likely to be where the mean is. Okay, whereas here, it's not that unlikely that a score is like over here, right? It's pretty far away from the mean. It's not, I mean, the probability for that happening is not that low. But let me actually exaggerate this graph a little bit more. If you take the average, the probability that the average is like that far away from the mean is much lower than the probability of one test being that far away from the mean. Okay, I'm hoping that I'm making some sense here. So when you take the averages, if you take random scores and then take the average of those scores, it's going to become more like a normal distribution. The scores are going to become closer to where the average is, and the extreme scores are going to be less. Okay, and you can think of this in a classroom setting. It's much more common to have like a 0% quiz or a 0% test, but it's very, very unlikely to have a 0% overall grade. Right? If you take the overall grade of each student, it's going to be more towards the mean average of the whole class. Okay, so when you look at the mean score, so the mean here, if you take the mean of the individual score, that was this, right? That was the class average. If you take the mean of the average scores, it's still going to be the same. The mean is still going to be the same. But the standard deviation is going to be different. As you can see at these two graphs, the individual, these are the individual graphs or individual scores, are much more spread out. And you can see that on this data set here as well. The scores are much more spread out, whereas if you take the average scores, they're much more towards the mean. They're closer to the mean. So the standard deviation is going to be bigger here than it is here. Because here, the data are closer to the mean, which means the standard deviation is pretty small. Okay, remember the standard deviation tells you the difference between the data and the mean, or roughly speaking. Okay, so if you know the standard deviation of the original data, meaning this data right here, you can find the standard deviation of the means here, okay, by using this formula. Remember that X bar means the mean. This is the mean. So this is the mean data set. When I say X bar, I'm talking about the mean data, or the average scores. I'm just talking X, it's just the individual scores here. Okay, so like I said before, the mean's going to be the same. So the mean of the original score is going to equal the mean of the average scores. And the standard deviation of the original score is going to equal, or I should say, the standard deviation of the mean scores is going to equal the standard deviation of the original score divided by the square root of n. Okay, and the n here means how many data did I find the mean of? So for example, for each of these means, how many data worth mean is that? And you can see for each of these data, I took 4 scores. right? There are 4 red scores, 4 blue scores, and 4 green scores. So I took the mean of 4 different tests here. So that means the n in this case would be 4. So let me just, I'm pretty sure that this is not actually correct, but let's say that the standard deviation here is 10. Then what would be the standard deviation of the means here? Okay, and we can find that by doing standard deviation of the means is going to equal standard deviation of the original data, which is 10, divided by the square root of 4. Right, the square root of 4, that's our n. So that's going to equal 10 divided by 2, which is 5. So you can see that the standard deviation for the mean scores is less than the standard deviation of the original score. Because, and you can see that even on the graph, that all the data are much more closely crowded towards the middle, towards the mean. Okay, so let me show you another example. Okay, I'm hoping that the second example would help you clear things up more. Okay, let's say that we took the temperature of a certain city. Let's say that these were the temperatures of that city during 1 month. And I'm doing these all in Celsius. And the temperatures are going to vary a lot throughout the month. 28 degrees, 31 degrees, 15 degrees, okay? I'm not putting these in any particular order, but let's say that this is the data that we've collected. Obviously, there's going to be much more than this. I'm just writing down 9 for the sake of time. Actually, let me add one more to make it nice, make a nice 10, okay? So I have 10 temperatures taken of a city during 1 month. Okay, and I'm going to have a mean for this data set, right? I can find the mean of this by adding them all up and dividing by 10. But if I take the average, so let's say that, or let me actually ask you a question. What would be the probability that the average of 5 temperatures is greater than 25 degrees? Notice that this is different from asking what is the probability that one temperature is greater than 25 degrees, right? If this is the question, then you can just find the mean and the standard deviation here and use the z-score. Minus 25 over standard deviation. Actually, I think these are switched. Right? That's how you'd find the probability that, or the z-score of, if it was the question was asking just a particular temperature being greater than 25 degrees. But here it's asking about the average. Okay, so here it's asking for the mean of the averages and the standard deviation of the averages. So to do this one, and we're taking 5 temperatures, right? We're taking 5 random temperatures, so that means n would equal 5. And this would be the same, right? We've shown before that that's the same as the original. And for the standard deviation, we'll have to just do that divided by the square root of 5 for the standard deviation. So you'll get your z-score this way if it's asking about the average. Okay, and in fact, this way is going to be much closer to a normal distribution than this would be. And also, as the n becomes bigger, the data has become more normal.